Hi, this is Dr. Habib Ahmed. I recently received a lot of emails regarding the Silvaco TCAD simulation of solar cells. So I'm hereby posting a video on the Silvaco TCAD simulation of 3 different material technologies based solar cells. First, I will demonstrate the Silvaco TCAD simulation of silicon solar cells, basically PIN structures. Secondly, I will demonstrate the Silvaco TCAD simulation of gallium nitride, indium gallium nitride based solar cells with multiple quantum wells. And finally, I will show the Silvaco TCAD simulation of gallium arsenide, indium gallium arsenide based solar cells. And let me briefly give you the idea of what is coming up. So for example, here is a silicon-based solar cell. It's a PIN structure. We have a p-type layer over here at the top, an I layer in the middle, and an n-type layer at the bottom. And I've labeled the anode and cathode in this structure as well. So I will perform the simulation of this structure. In this structure, the I layer thickness is approximately 10 micrometers. Then I will also show the results for I layer thickness of 20 micrometers and finally I layer thickness of 50 micrometers as well. Then I will focus on the Silvaco TCAD simulation of indium gallium nitride based solar cell, where I have kept the indium content to 20%. So for example, here you can see the structure. It has 5 quantum wells. Here is the meshing. Here you can see the doping. So we have the p-type layer at the top, an n-type layer at the bottom of the structure. And in the middle, I have how many? 1, 2, 3, 4, 5, 6 quantum wells of indium gallium nitride, separated by gallium nitride spacing layers, and I will demonstrate what is the functionality of the spacer layers and of the quantum wells. Then I've also performed the simulation for 10 quantum wells for the same structure. Then I will show the simulation of 30% indium in indium gallium nitride, and I will show the simulations for 5 quantum wells, and I will also show the simulation for 10 quantum wells. Later, I will also include an aluminum gallium nitride based layer in that solar cell structure and see how the aluminum gallium nitride layer, we also call it the barrier layer, affects the result of the solar cell structure. Finally, I will demonstrate the Silvaco TCAD simulation of gallium arsenide, indium gallium arsenide structures, as you can see over here. And here I've also included a few quantum wells of 20% indium in indium gallium arsenide. And then finally I will show the Silvaco TCAD simulation of 40% indium in indium gallium arsenide based solar cell, as you can see from the structure over here. And I'm going to show it in the code as well. So, excuse me. With these goals in mind, let us start the simulations. Before the simulations, I want to give a short brief on the basics of solar cells. And I'm not going to go into details because I have already posted a video on the theoretical understanding of solar cells, as you can see over here on my YouTube channel. For the simulation purpose, I will first run Silvaco TCAD. We go to File, Open. I've saved the file at desktop. And first I want to show the Silvaco TCAD simulation of silicon PIN structure based solar cell where the I layer thickness is 10 micrometers. So I will open the code, but as I often discuss that the font size in the deck build environment in Silvaco TCAD is really small. So I'm going to walk you through the code in Microsoft Office document, and after that we will run the simulation in Silvaco TCAD. We start the code with GoAtlas, and after that we define the meshing. So let me open a corresponding figure as well, showing the meshing and the structure, as you can see over here. Okay. Regarding the meshing part, our structure is running from 0 to 10 micrometers in the x direction and from 0 to 10 micrometers in the y direction as well. I have defined denser meshing at the top close to 0, and I've defined denser meshing at the bottom as well close to 10 micrometers. In the middle, I will define sparser meshing, and the reason for defining sparser meshing in the middle is that we have a thick I layer, while here at the top we have the p-type layer, and at the bottom we have a thin n-type layer. You can see the meshing over here as well. Denser meshing at the top and also at the bottom, and sparser meshing in the middle. Then we go to structure definition. The material is silicon. I will define the electrodes as well. Anode at the top running from 4 to 6 micrometers. So as you can see over here, here is the anode. It's more visible over here, running from 4 to 6 micrometers over here at the top. And the bottom of the structure is defined as the cathode. Then I save this structure and I name it as habibi.str. Then I run the command of GoAtlas once again. I import the same structure which is named as habibi.str. For the entire structure, I have introduced an n-type carrier concentration of 1 into 10 to the power of 14 per centimeter cube initially. Then at the top, close to 0, I introduce a Gaussian p-type doping with a carrier concentration of 5 into 10 to the power of 18 per centimeter cube. And this parameter relates to the Gaussian distribution of the carrier concentration of the doping. CHAR is equal to 0.1 means that our peak distribution would occur around 100 nanometers in this structure. Similarly, I introduce n-type doping at the bottom of the structure, represented by this number, which is 10 micrometers, and I have set its carrier concentration to n-type. Then I've introduced some material parameters. For example, our material is silicon, so I have set the electron and hole lifetimes to 1 microseconds. And also over here, this part is crucial. We know we are working on a solar cell. A solar cell is a device that directly converts the energy of light into electrical energy through the photovoltaic effect. So in a solar cell, the input is light energy, similar to a photodetector. In a photodetector, the input is light energy as well. And I have already posted YouTube videos on the theory and simulation of photodetectors. The functioning of a solar cell is similar to that of a photodetector, with some differences though. Solar cells are typically wide area devices to maximize exposure. Solar cells are meant as power sources, that is to convert light into power. We don't really care about speed in solar cells, while photodetectors on the other hand are intended to work as sensors or receivers, that is to convert light into a signal for detection purposes, for sensing purposes. Photodetectors are optimized for sensitivity and speed. Now, in both solar cell and photodetector, the input is light, and we know that when light enters the semiconductor structure, it's going to have some form of refraction and also some form of absorption. So with each material we need to associate two parameters, the refraction refractive index and the absorption index, and there are multiple methods to introduce these parameters for different materials. Silvaco TCAD database has these parameters built in for some materials. For example, for gallium nitride, for silicon, for gallium arsenide, for indium gallium arsenide, we already have these parameters included. And remember that refractive index and absorption coefficient, or we can also call it the extinction coefficient, is a function of wavelength. So it's not a single value. It's dependent on the wavelength of the input light. Now, this parameter over here, SOPRA, actually identifies the name of a file from a particular database. Their database is called the SOPRA database, courtesy of a company called SOPRA, which is a thin film technology company located worldwide. And these SOPRA files have refractive index and also the absorption coefficient of different materials plotted versus, or you can say listed versus the wavelength of the input light. So we can just pick that particular file from the database, and it's going to have the these material parameters, and we can just introduce them into our code. So for example, I'm working on silicon solar cell, and let me go to a particular file. I want to open the Atlas user manual. And I'm looking for SOPRA. So then I want to go to that particular section which talks about the SOPRA database. So here you can see for we have the commands for introducing the SOPRA files for different materials. For example, silver, and since right now I'm working on silicon material, so we go to that particular page which contains the information for silicon. Yeah, here it is. For silicon 100, we have to include this command. For silicon 110, we have to include this command. And then for silicon 111, we include silicon 111.nk. N over here represents the refractive index, and K represents the absorption coefficient. So we can include these commands in our code in order to call those files into our code. And we have them for a lot of materials, as you can see over here in this table, but we don't have commands for all materials. You can see it over here for indium gallium arsenide as well. But if you want to include indium gallium nitride film into your code, then we don't have a command for that. You actually have to create a file And in that file, we have to list down the refractive index and the absorption coefficient parameters versus wavelength for indium gallium nitride. And I'm going to show it to you later how to perform that. But as for now, you know that for silicon, we already have a command, and we just call that SOPRA file, which automatically includes the refractive index and absorption coefficient information versus wavelength for silicon. Then we introduce some models, for example, bipolar, Fermi, Shockley-Red-Hall recombination, field-dependent mobility, concentration-dependent mobility, OJ recombination, band-to-band recombination for direct materials, direct band gap materials, and the print command actually gives runtime output in Silvaco TCAD simulation. So we see the runtime output over here in this window. Then we include a method for the simulation purpose. There are several different numerical methods that can be used for calculating the solutions to semiconductor device problems. There are basically three types of solution techniques. They are Gummel, Newton, and Bloch. The Gummel method is useful where the system of equations has only linear convergence. The Newton method is useful when the system of equations has quadratic convergence. The Newton method may, however, spend extra time solving for different quantities. And the Newton method also requires a more accurate initial guess to the problem to obtain convergence. Bloch method, on the other hand, can provide for faster simulation times, in these cases over Newton. So one particular approach could be, since we know that Gummel can often provide like better initial guesses to problems, so it is useful to start a solution with a few Gummel iterations to generate a better initial guess, and then switch to Newton to complete the simulation. So specification of that particular solution method can be carried out using these commands. And then maxtrap gives the number of iterations that we can use in order to obtain conversion if we are facing convergence problems. In this case, we are actually giving it like 20 number of iterations. Then we are using the output command. So here we can look at the optical intensity, some band parameters, for example, conduction energy level, valence energy level, polar charges, some band parameters, electron and holes mobility, Shockley-Red-Hall recombination, radiative recombination, OJ recombination, permittivity, etc. And after that, I want to plot the structure. For the structure, we need an initial guess. We save the structure using this command, and then we plot the structure using the Tony-plot command. Then in solar cell characteristics, we know that we would like to look at the IV characteristics of the solar cell, the current voltage characteristics of the solar cell under dark conditions and then under light conditions. So here first I have included a block for looking at the IV characteristics of the solar cells under dark conditions. So I'm creating a log file with this name, and then I sweep the voltage from 0 to 0.55 volts. I've already run the simulation for this structure, and I know that the open circuit voltage for this structure is around 0.5 volts. So I'm running the sweep from 0 to 0.55 volts with a step of 0.01 volts. And then I enter a log off, so that this log file does not interfere with the upcoming log files. And at this point, we need to include a beam. We need to include the solar, since it is a solar cell and the input is going to be solar spectrum. So here we are actually referring to a beam. We call it beam number 1, AM 1.5. which represents the solar spectrum at the Earth's atmosphere at an angle of 48.2 degrees. So, and then we say that this beam is originated at 5 micrometers along the x direction and minus 2 micrometers along the y direction at an angle of 90 degrees. So we are actually introducing a beam over here, like in the center and slightly above the top surface of the structure. Okay. And then so let us talk a little bit about the AM 1.5. We know that the solar spectrum typically extends from the infrared range to the ultraviolet range, where the wavelength ranges from 0.2 to approximately 3 micrometers. But the intensity is not uniform in this entire wavelength range. For example, here is the solar spectrum that you can see over here, running from approximately 0.2 to 2.5 micrometers. And here the yellow part is the sunlight without atmospheric absorption, or you can see sunlight at the top of the atmosphere. And we can see that it can be approximated actually with black body radiation at a temperature of approximately 5250 degrees as well. There is also a difference in spectra measured at the top of the atmosphere and at the surface of the atmosphere due to atmospheric scattering. It's not given over here, but this red spectrum is actually the spectra measured at the Earth's surface, and we see the intensity is not uniform. You see dips at different wavelengths as well due to atmospheric scattering and absorption. Now, the path length of the light in the atmosphere depends on the angle, which will vary with the time of the day. And that is given by the ear mass number, which is secant of the angle between the sun and the zenith, or between the sun, the light coming from the sun, and the vertical direction. So we call it a secant theta. So the ear mass number is given by AM secant theta. Now AM0 represents the solar spectrum outside the Earth's atmosphere. AM1 is when the angle is 0, that is when the sun is at an angle of 0 degrees right above the Earth's surface. And AM2 is when the sun is at an angle of 60 degrees. Similarly, AM1.5 is when the sun is at an angle of 48.2 degrees. We have standard test conditions for measurement of solar cell parameters, and according to the standard test conditions, the solar cells need to be measured at room temperature, room pressure, and at AM 1.5, which is 48.2 degrees from the zenith. So we introduce this beam, we introduce the solar spectrum, then we make some initial guess for the extraction of the solar cell parameters. We know that the first step is to illuminate the device, and we can turn on the illumination by assigning the beam intensity on a solve statement, like you can see over here. So as we had assigned AM 1.5 on the beam statement, this corresponds to standard test conditions. In some cases, we may encounter convergence difficulties, and we may need to ramp up the light intensity as given over here. So we know this, according to the standard test conditions, the intensity should be 1 kilowatt per meter square, represented by this. But we may face convergence problems, so it's a better idea to start the intensity with a smaller value. So we are starting with 1 watt per meter square, then we ramp it up to 10 watts per meter square, then we ramp it up to 100 watts per meter square, and finally we ramp it up to 1 kilowatt per meter square. Then we create a log file, and I have named it as Habib_light, in order to save the IV characteristics of the solar cell under light conditions, which is the next step to extract the illuminated forward current voltage characteristics. And for that purpose, first we need to define an output file in order to capture the data. And this is that file, Habib_light. Now, this specifies that all the current voltage characteristics need to be extracted from the solve statement and will be captured in Habib_light.log in the current directory in which we are actually running the code. Now, here I am running a sweep from 0 to 0.55 volts, and as already discussed that I know that the open circuit voltage is around 0.5, so running the simulation up to 0.55 should be enough. And I have introduced a smaller step because I want to have good accuracy around the open circuit voltage. From that point onward, when the sweep is complete, we can plot the dark IV characteristic and the IV characteristics of the solar cell under light, and we can overlay them in a single plot using this command. And then I save the structure once again with this name, and then I plot the structure. Now here, since I have saved the log file now under light conditions, I call that file once again using this command, extract init in file. So I'm calling this file, and now after calling this file, I actually want to extract different parameters. For example, the short circuit current density. We achieve JSC when for the IV characteristic we have an X value of 0. When the voltage is 0, we achieve the short circuit current density, and then we convert it into milliamps per centimeter square using these commands. I'm also extracting the open circuit voltage, and we achieve the open circuit voltage for a Y value of 0. So when the current is 0, we achieve open circuit voltage. Then we know that power is the product of the anode voltage versus anode current, and we also have a maximum power point in this curve, so we extract that parameter as well, and we can extract the maximum voltage, we can extract the maximum current as well. We can extract the fill factor, which is actually the fill factor is the we have a formula for that. It's equal to the maximum voltage times the maximum current divided by open circuit voltage times short circuit current. And then so here it's equal to PM, which is the product of the maximum voltage times the maximum current divided by open circuit voltage times short circuit current density into 100. Also we can extract efficiency as well. Efficiency is the output power divided by input power. The output for a solar cell is electrical, so it's the product of the output current times the output voltage, and the input is optical, which in our case is light intensity times the area of the device. So then we plot the power curve as well. Then we start another block of Atlas code, and we input the structure which we already simulated in the previous block code. So for example, here you can see after running the IV characteristic under light conditions, I've saved the structure with habib4.str, and in the next block I am importing that structure once again with this command of mesh in file, and after that I assign some material parameters, and we set the beam conditions. Then I want to look at some output parameters, models, which we already discussed in the previous section as well. Then I create a log file in order to look at the spectrum of this solar cell, in order to look at the cathode current or the available photocurrent versus wavelength for this particular solar cell. We introduce these commands in order to have an initial guess of the sweep, and then we use solve command. B1 represents beam number 1 is equal to 1 kilowatt per meter square. And we are running the sweep from 0.3 to 1.5 micrometers. So we want to look at the spectral response in this range. And then we plot this spectrum. Next, after saving the results in habib5.log, I'm calling that file once again in order to determine the internal quantum efficiency and the external quantum efficiency, which is anode current divided by the source photocurrent, and then the external quantum efficiency while including the absorption effect as well. And finally, we plot the internal quantum efficiency EQV and EQV2 in the same graph using the overlay command, and then finally we get the code. So now I'm going to run the simulation. Here is my structure running from 0 to 10 micrometers in the x direction, and also running from 0 to 10 micrometers in the y direction. We can look at the meshing as well. So I right click on the structure, then click on display, click on meshing. This gives me the meshing. As I already discussed, that we have defined a denser meshing here at the top and also at the bottom, but sparser meshing in the middle. We can also look at the contacts by clicking on this icon, hit apply. So we have anode over here running from 4 to 6 micrometers in the x direction, and the bottom side of the structure is assigned as cathode. I uncheck the meshing. And then we can also look at the dopings inside the structure. So we click on contours, then we go to define, click contours once again. We select absolute net doping, hit apply, and click OK. So here now we see the doping levels inside the structure. As we can see that we have introduced high doping level at the top and also at the bottom, but lower doping levels around 10 to the power 14 per centimeter cube in the middle. As you can see from the color chart as well. Or there is another way to look at that as well. So if we draw a cut line right across all the structure, or we can say the entire structure, draw a cut line across the entire structure, then we see the doping levels over here as well. Around 5, 10 to the power 18 close to the top and also at the bottom, but 10 to the power 14 in the middle. Also, we can right click on this plot, go to display, and we can look at the conduction energy level, valence energy level, electron quasi-Fermi level, and hole quasi-Fermi level for this structure as well. Hit apply, and now this is our energy band diagram for this structure. You can see that the Fermi energy level, and this is under thermal equilibrium. You see that the Fermi energy level is close to the conduction band on the right. So over here on this side we have the n-type material, and here it's close to the valence band, so we have the p-type material on this side, and in the middle we have the I layer. As you can see over here, it's obvious. Excuse me. Then these are the simulated results, but first I want to look at the structure. So this is Habib 4.str. This is the structure under light conditions. So if we go to display, and after we go to display, we click on contours, we go to define, and then click on contours once again. Then we can look at photo generation rate under light conditions. We hit apply. So and then if we zoom in on the contact, like we see that under the contact the photo generation rate is really small, and we can optimize the structure further as well. I want to zoom in, and also we can draw a cut line to look at the exact photo generation levels across the structure. So for example, I draw a cut line over here across the entire structure, and we see that the photo generation rate is decreasing from approximately 2, 3, 4, 5, 6, 10 to the power of 21 per centimeter cube to approximately 10 to the power of 20 close to the bottom of the structure. We can also look at the absorption rate across the structure. For example, I need to click on this one first and then go display, contours, define, photon absorption rate, hit apply. So now you see the photon absorption rate across the structure, and we can also see that over here by going to display, unchecking photo generation rate and checking the photon absorption rate, and then I hit apply. So now you can see that the absorption rate is really high, close towards the top, around 5 into 10 to the power of 21 per centimeter cube, but it exponentially decreases as we go further down along the structure. And this is because of the absorption coefficient. We know that there is going to be photo generation inside the structure. Now the total width of the region that contributes to the solar cell current is the, let me go to a particular figure, for example this one. So the total width that contributes to the solar cell current is the width of the I layer, represented by this purple color, plus the diffusion lengths in the p-type layer of electrons in the of holes in the p-type layer, and the diffusion length of the diffusion length of electrons in the p-type layer, and the diffusion length of holes in the n-type layer. So it means that if light is absorbed inside the I layer, it's going to result in the generation of electron-hole pair. Electron travels down to the n-type layer, and hole travels up to the p-type layer. So most of the photo generated carriers inside the I layer would contribute to the solar cell current. But now the question is, what about the carriers which are generated inside the p-type layer or inside the n-type layer? So for example, consider the p-type layer. If an electron-hole pair is generated, then the hole is going to travel towards the p-type contact. For electrons, since we have a lot of holes over here in this region, there is a high chance that this electron may recombine with the holes in the p-type layer. So then if this electron hole pair is generated within the diffusion length of the electron, which is the length of the electron that it can travel before it recombines with a hole. So if it is generated within the diffusion length, it's going to travel towards the I layer and then towards the N-type layer. Similarly, for this layer, for the N-type layer, if an electron hole pair is generated, this electron hole is going to contribute to the solar cell current only if this is generated within the diffusion length of the electrons. If this is generated within the diffusion length, this electron is going to travel towards the hole is going to travel towards the I layer, and from that point onwards towards the P-type layer. So this is all about that. And after that, these carriers are actually extracted by the metal electrodes on both sides. So that part is covered. Talked about the absorption. After this, let us look at the IV characteristic. The red curve represents the IV characteristic under dark conditions, and the green curve represents the IV characteristics of the solar cell under light conditions. And the point where this green curve crosses the zero axis gives us the open circuit voltage, and the point where it crosses the y-axis gives us the short circuit current. So the y-intercept of this green curve gives us the short circuit current, and the x-intercept of this curve gives us the open circuit voltage. And we can zoom in on this and look at exactly these values, but it's already calculated inside the program, so I'm not going to manually do. We are just going to look at the results. Similarly, we have the power curve where we have the maximum power point, the point where the product of the voltage and current gives us the maximum value. And we generally operate the solar cell at the maximum power point. And once again, the maximum power is also calculated by the code, so I'm not going to manually look at this point and figure it out. I'm just going to show you the results. The quantum efficiencies in spectral ranges are also simulated. But before that, I want to go to the output runtime window. And inside this window, I'm gonna go up to the point which gives us the open circuit voltage, short circuit current, and other parameters. So here are my crucial parameters. The short circuit current density, then the short circuit current density in milliamps per centimeter square. The open circuit voltage for this structure is 0.52, approximately 0.52 volts. Here is the maximum power, maximum voltage, maximum current at the maximum power point. Our fill factor is approximately 74.9, and our efficiency for this structure is approximately 17.1%. Similarly, we can look at the spectral range for this structure. So I right click on the structure, go to display, and then I click on optical wavelength, hit apply. Here is the spectral response of this solar cell. For the silicon solar cell, it kind of matches with the AM 1.5 solar spectrum, as you can see over here. So the range is approximately from 0 to, you can see, 1.5 micrometers. It's still continuing. I have not plotted it beyond 1.5. So you can plot it like above 1.5 to look at the exact spectral response of this solar cell structure. And finally, we can also look at, by the way, talking about the spectral range, the spectral range depends on two parameters. The upper cutoff wavelength is determined by the band gap of the material. For example, for silicon, the band gap is 1.12. And according to a simple formula, energy band gap is equal to Hc divided by lambda, or you can say 1.24 divided by lambda in micrometers. Its upper cutoff wavelength is going to be 1.1 micrometers. For germanium, the band gap is 0.67, so the upper cutoff wavelength is approximately 1.85. For gallium nitride, the band gap is 3.4 electron volts, so the upper cutoff wavelength for gallium nitride is 0.365 micrometers. Similarly, the lower cutoff wavelength for a solar cell is determined by the absorption coefficient of the material. And we saw over here in this structure, the lower cutoff wavelength was approximately 0.3 micrometers or 300 nanometers. So here is the quantum efficiencies. We go to display to look at EQV and also EQV2. We hit on apply. And then we zoom in on these curves over here. You would like, let's say, in this range. So here our internal quantum efficiency is represented by the red curve. The green curve gives us EQV, and the blue curve gives us EQV2, in which we have also included the effect of the absorption. And as you can see that EQV and EQV2 are lower as compared to the internal quantum efficiency, would say above 0.5 micrometers. Experimentally, it should be lower over here in this range from 0.4 to 0.6 micrometers. But I need to look deeper into this code in order to further optimize it. And now, I showed you this simulation of the PIN structure where the I layer thickness is 10 micrometers. And as I already discussed, that the spectral range is a function of the band gap of the semiconductor and also the absorption coefficient. Now our solar spectrum runs from 0.3 to approximately 3 micrometers, or 0.2 to 3 micrometers, right? So it has shorter wavelengths, it has medium wavelengths, and it has longer wavelengths. Shorter wavelength light has materials have higher absorption coefficient for shorter wavelength light. So shorter wavelength light can travel only shallower into the material, so you can say close to the top surface. Similarly, medium wavelength light can travel up to medium distance inside this structure, and longer wavelength light can travel deeper into the structure. For this structure, the I layer thickness is 10 micrometers, but I also performed the simulation for 20 micrometers I layer thickness. As you can see over here, this structure is running from 0 to 20 micrometers. And then I also performed the simulation for approximately 50 micrometer I layer thickness. And I compiled all the results, but I have combined together, I have combined the results together, the crucial results together in this slide. So here is a comparison of 10 micrometers, 20 micrometers, and 50 micrometers I layer thickness based silicon PIN solar cells. For comparison, we can see that the current density increases from approximately 43 milliamps per centimeter square to approximately 54 to approximately 59 milliamps per centimeter square. So with increase in I layer thickness or short circuit, current density increases, and this is because with the larger I layer thicknesses, we are able to absorb the longer wavelength light as well, resulting in more photo generation and correspondingly result in higher short circuit current density as well. Now if we compare the open circuit voltage, It slightly decreases, but there is not a big difference for the three structures. Similarly, since the short circuit current density increases as we increase the I layer thickness, the maximum power also increases as we increase the I layer thickness, maximum achievable power from the structure. And similarly, since efficiency is equal to the output power divided by input power, where the output power is the product of the voltage and current. So since the current increases, the efficiency also increases as we increase the I layer thickness from 10 to 20 to 50 micrometers. The efficiency increases from 17 to 20 to approximately 21% as we increase the I layer thickness from 10 to 20 to 50 micrometers. Now that's it about the silicon PIN solar cells. Now I want to demonstrate the simulation of gallium nitride, indium gallium nitride based solar cells. The first blue LEDs were achieved by utilizing gallium nitride, indium gallium nitride based structures, and these LEDs have a significant role in the market. So I wanted to simulate indium gallium nitride based structures as well. Now here is the structure, and let me open the code for the gallium nitride, indium gallium nitride solar cell as well. I've also copied it into a Word file, so I'm going to open the Word file so that I can walk you through the code in a comfortable way. Otherwise, there is going to be some sort of blurring if you just look at the Silvaco TCAD environment. So here is our code. I've defined a structure which runs from 0 to 10 micrometers in the X direction and from 0 to 5 micrometers in the Y direction. Then I have defined denser meshing from 0.050 to 0.120. You can see from 50 nanometers to 120 nanometers I have defined denser meshing. So if you look at the structure, this layer over here represents the P-type gallium nitride film running from 0 to 50 nanometers. Then from here, from 0.120 to 5 micrometers, which is not shown over here, I have the N-type gallium nitride layer. And from 0.050, this number over here, to 0.120, up to this point, I have included multiple quantum wells of indium gallium nitride films. And for this region, since this is our active region, we will have more photon absorption in this region. I have defined denser meshing, while for the rest of the structure, I have defined sparser meshing. And here is a zoomed in version of the same structure. As you can see at the top, I have the P-type layer. Over here at the bottom, I have the N-type layer. And from 0.050 to 0.120, I have included multiple layers of indium gallium nitride and gallium nitride films, which is going to be more obvious as we walk through this page. So my first region runs from 0 to 10 micrometers in the X direction and from 0 to 0.050 in the Y direction. As you can see over here, from 0 to 0.050. And I've set the doping of this later, but this is my P-type gallium nitride layer. My second layer is indium gallium nitride with an indium content of 20% or an X fraction of 0.2. It's running from 0.050 to 0.053 in the Y direction. So this film over here is just 3 nanometers indium gallium nitride film with 20% indium content in the indium gallium nitride layer, and I have defined it as a quantum well. After that, my region number 3 is a gallium nitride film running from 53 nanometers to 63 nanometers. So after this thin indium gallium nitride film, I have introduced a 10 nanometers undoped gallium nitride spacing layer, or we can call it a barrier layer as well, and you can see it in the energy band diagram why it is called barrier layer. After that, I've included another 3 nanometers film of indium gallium nitride with an indium content of 20%, another spacing layer, another quantum well layer, another spacing layer, another quantum well layer, another barrier layer, and so on. So in total, I've included 6 quantum wells inside this structure. And finally, my region number 13 is running from 0.118 to 5 micrometers, and later I have set its doping to N-type. So this bottom layer over here, I have not shown the entire structure, but it's running from here up down to 5 micrometers. Then I have set the top electrode to anode and the bottom electrode to cathode. Then I am saving this structure with this name. It's a lot of the rest of the code is similar to the one shown in the silicon structures, so I'm not going to the details of all of them. Then I run the command go atlas, and I have imported that particular structure once again. I've set the doping of region number 1 to p-type and region number 13 to n-type, as already discussed previously. So this top layer is my p-type layer, and this bottom layer is the n-type layer. After that, I need to set some material parameters. For example, for gallium nitride, I have defined the electron and holes recombination lifetimes, and these are not the exact lifetimes, and I mean generally the lifetimes are for carriers are lower in gallium nitride because of experimental reasons. And then I have included a SO profile for gallium nitride, which contains the refractive indices and the absorption coefficients information for gallium nitride film versus wavelength. So that means it's not going to be a constant value. The refractive indices and the absorption coefficients will vary as a function of the wavelength. Then I have included another layer, which is indium gallium nitride, and I've set the parameters for this layer as well, the electron recombination lifetime and the hole recombination lifetime. Now here is the most crucial part, and it took me some time to figure it out. So as I already discussed, that we have SOPRA files in the database of Silvaco TCAD for a lot of materials, for gallium nitride, for silicon, for gallium arsenide, for indium gallium arsenide, but we don't have that information or those files in the Silvaco TCAD database for indium gallium nitride. So it took me some time to figure out how to include the refractive indices information and also the absorption coefficients information into my code. How to include it into my code, because this part is crucial. We are dealing with light, which is our input, and our material is going to have some refractive index and some absorption coefficient is a function of the wavelength. We are not working with a single wavelength either. We are working with a solar spectrum. So I needed to do some work on that, and I was able, at the end of the day, I was able to figure it out. So what I did is that I found a paper And inside this paper, we have couple of plots. This plot gives the refractive index information for indium gallium nitride. As you can see, we have like indium 0.1 gallium nitride and indium 0.2 gallium nitride, 0.3, 0.4, 0.5, 0.62, etc. And I was working on two structures, indium 0.2 gallium nitride and indium 0.3 gallium nitride structures. So we have the refractive index information versus photon energy and the absorption coefficient versus photon energy information for these films. Excuse me. And what I did is that, let me go back to that particular directory. Not this one. So I copied these figures. This is the refractive index versus the photon energy. I converted the energies into wavelengths. So now this is the refractive index as a function of the photon energy, 0.3 to 1.2 micrometers. And then at each of these points, 0.3, 0.35, 0.4, I figured out the corresponding refractive index for the Sion curve, which is for 20% indium gallium nitride, and I listed them down in a particular file. And then also for indium 0.3 gallium nitride, and I noted them down into another text file. Similarly, I collected that information for the absorption coefficient as well for indium 0.2 gallium nitride, which is the Sion curve, and for indium 0.3 gallium nitride for these values, which are like 1, 2, 3, 4, 5, 6, 7. Ideally, I needed to do it like for 100 samples, but that was going to take forever. So I just noted them down for 7 values, and after that, I entered the same information in this file. So this 7 over here tells me about the number of samples. As already discussed, I collected the information for 7 wavelengths, 7 data points. So this number gives the number of samples. Then this first number in the next line gives the wavelength. The second number accounts for the refractive index, and the third number represents the absorption coefficient. So I listed down these ordered triplets for these 7 different wavelengths, and I called this file as in2 GaN file, and this is a .nk file where n represents the refractive index and k represents the absorption coefficient. So I saved this information, and then I'm running this code from the same directory. So as you can see, I've indexed this file, I've called this file to include the optical properties into my code. After that, I've included the models, the methods, output, and then saving the structure, plotting the structure, plotting the IV characteristics. Now I've run the sweep from 0.0 to 3 volts since we are dealing with gallium nitride. And my open circuit voltage is somewhere in this range, in the range of 1.6 to 2.6 volts. So in this range, I have defined a smaller voltage bias. And then I've entered the information for beam number 1, which is my AM1.5 solar spectrum. We ramp up the beam from 1 watt per meter square to 1 kilowatt per meter square. We save the log file for light conditions as well, and then I've run the sweep once again from 0 to 3 volts, and then I've plotted the dark IV characteristics and the light IV characteristics for this solar cell, and then I save the structure and then I plot the structure. And here this part is the same as the previous code for the silicon structure. So basically this block is used for looking at the short circuit current, fill factor, open circuit voltage, etc. We plot the power curve as well. I import the structure simulated in the previous code over here. I call the SOPRA files once again for gallium nitride and also for indium gallium nitride. For spectral range, I'm running the sweep from 0.3 to 1 micrometers. Then I plot the internal quantum efficiency, external quantum efficiency, etc. for this code as well. Okay, so that's all about the code, and here is the code. So I'm gonna run the code, but this is a really extensive program, and running this simulation takes approximately 1.5 to 2 hours. So I'm not going to sit here and run the simulation for 1.5 to 2 hours. I have already saved the results, and I'm going to right away show you the results. I mean, the structure part is like, okay. The structure part under thermal equilibrium is already simulated. It does not take a lot of time up to this point, but beyond this point it takes a really long time to get simulated. Here is our structure running from 0 to 10 micrometers in the x direction, 0 to 5 micrometers in the y direction. And then here is my active region. Before that, let me zoom out and show you the meshing. Denser meshing around the active region and sparser meshing in the rest of the structure. Okay, let me show you the active region where I have different layers of indium gallium nitride. So these purple layers actually represent indium gallium nitride, where I have introduced 20% indium in the indium gallium nitride layers, separated by the spacing layers. This layer over here is the p-type layer. This layer over here at the bottom is the n-type layer. I can display the contact as well. And then so then we can look at the energy band diagram of this structure right around this region. Instead of manually doing it, I'm just going to walk you through the saved figures. So I'm just going to open the figures. So here is the structure, the entire, not the entire structure. Here is the meshing. As you can see, it's denser around the active region. Then here is the p-type layer, n-type layer at the bottom, the active region over here. These are the indium gallium nitride layers separated by gallium nitride spacing layers. Here is the energy band diagram of the same structure under thermal equilibrium. We have the Fermi energy level is close to a valence band on the left side, so we have the p-type layer over here and the n-type layer on the right. In between we have quantum wells. So as you can see over here, this is a quantum well of indium gallium nitride layer, separated by a gallium nitride spacing layer. So over here, this one corresponds to the gallium nitride spacing layer, and then another quantum well another spacing layer, another quantum well, another spacing layer, another quantum well, another spacing layer, quantum well, spacing layer, quantum well. Here is the photo generation rate across the structure, and then I zoomed in on the active region as well for the photo generation rate. Looking at the color chart, you can see that the photo generation is higher for the indium gallium nitride layers as compared to the gallium nitride layers, and it's more obvious on the zoomed in figure over here. Here is the here is the photo generation rate via a cut line. So as you can see that the photo generation rate is higher in the indium gallium nitride quantum wells. Here is the figure for the absorption, photon absorption rate, and looking at the color chart, you can see once again that the absorption rate is higher in the indium gallium nitride layers. And similarly, we can see the same effect in this figure as well, where the absorption rate is much higher in the indium gallium nitride layer. And that is because the band gap of gallium nitride is 3.4 electron volts. The input light is the solar spectrum, right? Now the solar spectrum runs from UV to infrared, and for gallium nitride only the UV part of the light is going to be absorbed, but not the rest of the light. Now when we include indium gallium nitride, we decrease the band gap from 3.4 to a lower value. So now a higher part of the solar spectrum is going to be absorbed inside the indium gallium nitride layers, and that's why we have higher absorption rate and higher photo generation rate inside the indium gallium nitride quantum wells in the indium gallium nitride solar cell structure. This is the energy band diagram under light conditions for the same structure. Here is the IV characteristic under dark and light conditions for the same structure, the power curve, then the figures of merit for the solar cell, the spectral response running from approximately, you can say, 0.1 to 0.6 micrometers, the internal and external quantum efficiency. As you can see, the external quantum efficiency is much lower as compared to the internal quantum efficiency. The external quantum efficiency is approximately 10% over here at this point. But we also have an integrated internal and external quantum efficiency. So we care more about that part. And then looking at the figures of merit, the short circuit current density is 1.65 milliamps per centimeter square. The open circuit voltage is 2.356 volts. The fill factor is approximately 41.5, and the efficiency is approximately 1.6% for this structure. The program is still running and it's going to run forever. So I mean it's going to take like 1.5 to 2 hours. So I'm not going to run the simulation, this simulation any further. I will kill the simulation and I will show you some results. So like over here, in the structure that I have shown, I have included 5 quantum wells, but I also performed simulation of another structure where I included 10 quantum wells. Here is that structure. As you can see, in this structure I have included more quantum wells. And then I wanted to compare the results of this structure with the previous one. So here is a comparison of the 5 quantum well versus 10 quantum well structure. And we see that the open circuit voltage is approximately the same, but the short circuit current density has decreased for the 10 quantum wells. And correspondingly, the efficiency has also decreased from 1.6% to 1.2% as we increase the number of quantum wells in this structure. So these are just like rough simulations. I have not optimized the structure, but we would like to optimize the structure in order to achieve better results. Similarly, I performed simulation of another structure where I included 30% indium in the indium gallium nitride layer. Going to another folder, for example, this one, where inside the code, as you can see, for the indium gallium nitride layer, I have set it to 30% for the indium gallium nitride quantum wells. And I compared the result of 30% indium in the indium gallium nitride layer to the 20% ones for 5 quantum wells for each structure. And we see that with increase in the indium content in the indium gallium nitride layer, once again, the efficiency has decreased from 1.61 to 0.13%. So it's less than 1% now. And that's because the open circuit voltage, not a big difference, but the short circuit current density has decreased from 1.65 to 0.073 milliamps per centimeter square as we increase the indium content. And this potentially is because it's experimentally it's not easy to grow 30% indium gallium nitride as compared to 20% indium gallium nitride. I mean, there are groups in the world, like for example, one of the world famous groups is Dr. William Allen Doolittle's group at Georgia Institute of Technology, and they are able to grow indium gallium nitride films over the entire alloy range. But a lot of other groups are still not able to experimentally grow indium gallium nitride over the entire alloy range. But generally, it's still difficult to grow indium gallium nitride films with higher indium content. So I've shown this, and I've shown the comparison. And then here I also performed another simulation for 10 quantum wells for the 30% indium gallium nitride films, and I compared with the 5 quantum well one for the same indium content, and we see as we increase the number of quantum wells, the efficiency has further dropped to approximately 0.01%. Because the short circuit current density has further decreased as we include more number of quantum wells. Then I worked on another structure as well, roughly, and that structure is given over here. So it is aluminum gallium nitride, indium gallium nitride. So for this structure, the top layer is still p-type gallium nitride, and then running to like 50 nanometers, and from that point onwards, like from 0 to 50 nanometers, we have the p-type gallium nitride layer, and then from 50, not micrometers, nanometers, 0 to 50 nanometers. From 50 to 70 nanometers, I have included an aluminum gallium nitride layer with an aluminum content of 20%. And I have set it to p-type aluminum gallium nitride because this layer is close to the p-type gallium nitride layer. Similarly, after the active region, I have included another electron, this is called the electron stopping layer. And this is called the hole stopping layer from approximately 138 to 158 nanometers. And I have set it to N-type. I've set the doping to N-type for this aluminum gallium nitride layer. And I performed a simulation. I have saved all the results, corresponding results, etc., the spectral range and the internal and external quantum efficiencies, etc. But for comparison, with the inclusion of the aluminum gallium nitride layers, we see, and I want to show like the energy band diagram as well. So generally the goal of including these layers is, for example, if electrons are generated in this active layer, this acts as an electron stopping layer because it has a higher barrier height. So electrons would not be able to easily move towards the left, they would easily move towards the right. Similarly, this layer over here is the aluminum gallium nitride layer, which is p-type, is called the hole stopping layer. It has a big barrier for holes, so holes would not be able to easily cross this barrier, but they can easily move towards the left. So that was the goal of these layers, but the problem is that aluminum gallium nitride has a higher band gap than gallium nitride layer, so resulting in a larger open circuit voltage as compared to a structure which has just indium gallium nitride films, but it would result in a lower short circuit density as well. So the inclusion of aluminum gallium nitride films results in a much lower short circuit density, leading to much lower efficiency as compared to the previous structures. We can optimize the structures even by the inclusion of the aluminum gallium nitride layers. We can still improve the efficiency, but by further optimizing, we need to play around with the structures. Now, finally, I performed the simulation of indium gallium arsenide based solar cell as well, given over here. I've copied the code into a Microsoft Word file as well. So as you can see here, once again, it's running from 0 to 10 micrometers in the x direction, 0 to 5 micrometers in the y direction. It's similar, the structure is similar to the indium gallium nitride solar cell. Or I can show it to you. I've simulated the results. So here it is. I've included like 1, 2, 3, 4, 5, 6 quantum wells of indium gallium arsenide separated by gallium arsenide layers, as you can see from this color chart, from this legend as well. At the top I have the p-type gallium arsenide film, and at the bottom there is the n-type gallium arsenide film. And then here is the energy band diagram, the photo generation rates, the photon absorption rates, which are higher in the indium gallium arsenide layer. The band gap of gallium arsenide is approximately 1.4 electron volts, while the band gap of indium arsenide is approximately 0.35 electron volts. So we can tune the band gap from 0.35 to 1.4 electron volts for the indium gallium arsenide films. And for these films, I have actually included a gallium content of 0.8, or you can say an indium content of 0.2 or 20% indium. And then, as you can see, I have 6 quantum wells for the indium gallium arsenide. The rest of the code is the same as the previous structures. I'm not going to run through the entire code. I'm just going to show you the results. Here is the photon absorption rate, the power curve, the dark and light IV characteristics. Here is the spectral response, and here is the IQV and EQV. These are the figures of merit. I also run another structure based on the same materials, gallium arsenide and indium gallium arsenide, but for this one I have set the indium content to 40%. Once again, I'm not going to show you all the figures, but I've compiled the crucial results over here. structure based on 20% indium gallium arsenide versus structure based on 40% indium gallium arsenide quantum wells. So for the 20% indium gallium arsenide, we have a short circuit current density of approximately 16 milliamps per centimeter square, while for the 40% it has decreased to, so no, it's the same. The current density is almost the same. However, the open circuit voltage has decreased from 1.1 to approximately 0.95 for the 40% indium gallium arsenide. And this is because higher indium content would result in a lower band gap for the indium gallium arsenide, resulting in lower open circuit voltage for the structure based on these quantum wells. And then because of that, the efficiency has also decreased for the 40% indium gallium arsenide films as compared to the 20% indium gallium arsenide films. So I tried to cover various structures and various materials for this Silvaco TCAD simulation tutorial on solar cells, and I hope this comprehensive tutorial is really useful for you, because I consider it not a basic tutorial, but you can say I consider it as a research level tutorial where you can include more materials, even like new materials. I already posted videos on new materials. So by watching those videos, how to include new materials into Atlas tool and how to include new materials into the Athena tool of Silvaco TCAD, you can combine those videos, those codes with this one, and you can work on organic solar cells, you can work on perovskite solar cells, and a lot of other kind of solar cell structure. I wish you all the best for your research. Let me know if you have any queries. Thank you, take care, and adios.